So without further ado, we'll start. So private set intersection refers to the problem, typically with two parties, where they each hold a set, X and Y, and they wish to learn which items are in common to their two sets, while at the same time hiding items that are unique to only their set. So in this talk, I'll refer to a sender and a receiver, and we'll just assume that only the receiver learns any information at all, and the sender learns nothing. And so private set intersection has many applications. So highlighted here are some of my favorites. One that's actually being used by Google is shown here, where Tesla, for example, has paid Google for some advertising space on Google's AdWords. And as such, Google has a set of users who've seen the Tesla advertisement, while Tesla, on the other hand, has a big list of people who have purchased their latest and greatest car. And so Tesla would like to know whether their investment in Google advertising has been worthwhile. And so they'd like to figure out how many people have both bought a Tesla car and seen the advertisement. And so here, these list of people who are on these lists is quite sensitive. And so they don't want to just reveal them in the clear. And so these two companies can run private set intersection between them and only learn the people who have both seen the ad and purchased the car. And another example that's made the news, not necessarily PSI, but the example itself is voter registration. So here, people can register to vote in different states, and occasionally they become double registered in two different states. And this is undesirable and illegal. And so, what we'd like to be able to do is identify people who are registered in both states. However, simply revealing these voter rolls in general is even the Trump administration had asked to do this, and I think every state said no. And so what you could do here is run private set intersection between the two states and identify the people who are incorrectly registered in multiple locations in a privacy preserving way. And PSI is also far from new. Going back to as far as 86, Meadows introduced a technique to compare two items using a Diffie-Hellman style approach. And this has subsequently been improved and even made malicious-secure, where if the parties try to cheat or learn additional information, they fail. And other techniques, such as one introduced by Naylor and Pincus in '99, use oblivious polynomial evaluation. And it too has been improved through a series of works and made malicious-secure. And yet again, there's other paradigms based on generic secure computation. Here you'd express your function, in this case set intersection, as a circuit, and then you can securely compute the circuit. And surprisingly, in 2012, Hong et al. Actually showed that this approach performed as well or better than many of these custom protocols that target this functionality specifically. Moving forward to 2013, Dong, Chen, and Wen introduced yet another approach based on Bloom filters and oblivious transfer. And this was recently extended to the malicious setting earlier this year at Eurocrypt. One of the few paradigms up to this point that hadn't had a malicious-secure variant was first introduced by Feijin in '96, and it uses oblivious transfer directly to encode items. And it was popularized by Pincus and et al. In 2014, where they showed how this approach can be combined with a hash table-based technique to get extremely efficient private set intersection. And this, although there have been subsequent papers that improve some of the performance, but this basic paradigm today is like the fastest semi-honest private set intersection protocol. And so in this work that I'm presenting now, we show how you can bring this protocol, which is extremely fast in the semi-honest setting, to the malicious setting with only marginal overhead. And this is by no means complete. Here's a list of a variety of sort of a histogram over the years of all the papers that I was able to find on private set intersection. So it's a rich literature, and looks like we slowed down there a little bit, but then we got right back into it. So it's been a fun problem to work on. So one of the basic building blocks that we'll use in this talk is known as oblivious transfer. Here, the sender has two messages, M0 and M1, and the receiver has a single bit X. And the receiver should learn the message MX while learning nothing about the other message, and the sender learns nothing from this interaction. While this appears to be like a pretty simple functionality, It's actually very powerful, and we have very efficient implementations for this, consisting of a couple called to a hash function. And so it motivates it as the basis for fast private set intersection protocols. However, in this talk, I'll be using a slight variant of private set intersection known as 1 out of n OT. Here again, the receiver has an input x, but now it's an index between 1 and n, and they learn the corresponding message, while the sender learns all the messages m1 through mn, where they're just randomly chosen by the functionality. And crucially here, n can be exponential in size, say to the power 128, and so we can't enumerate these, and instead we provide sort of a random access to them on the sender's part. And to denote this, I'll use this notation, dot in the box, to mean that that party can pick up any of the possible n messages, while x in the box refers to a specific message. And for the rest of the talk, I'll refer to them as encodings instead of messages. So x in the box is an encoding, randomized encoding of x. So now that we have the basics, we can show how you can compare two items, x and y, for equality. So not surprising, we'll use oblivious transfer here, where we provide y as input and receive an encoding of x, while the other party receives the full set of all possible encodings. And now to complete it, we simply have the sender pick out the encoding for their element x and send it over. And we now can securely compare whether the encoding of y equals the encoding of x. And correctness is pretty easy to see, since this encoding is sort of deterministic. If the x and y are equal, then so will the encodings. And security follows from the underlying oblivious transfer, in that all these messages are random and sort of not correlated with their actually true value. And so if y doesn't equal x, learning the encoding of x reveals no additional information. And so we can extend this equality check to set membership, where we want to see if an element y is in a set x. And again, we use oblivious transfer in the same way, but instead of sending over a single element, we can send over many different encodings. And now we simply extend the equality check for membership. And we even can sort of encapsulate this sort of interaction into this nice ideal functionality where a set x is provided and an element y, and the membership test is returned. So recently, or last year, Kolesnikov et al. Showed how you can efficiently instantiate this functionality with only a single oblivious transfer. So it's like one hash call per party. It's very efficient. And it's even been made malicious-secure by Oru et al. However, one limitation of this technique is that the communication computation is linear in the size of the set x. And so you could imagine you could repeat many membership tests once for each y in the set y. However, this would lead to a quadratic overhead in the communication computation. And we want these protocols to scale to sizes of millions of items. And so quadratic overhead is just completely unacceptable. Pincus, Snyder, and Zoner in 2014 showed how you can reduce this quadratic overhead using a hash table technique. So here we sample a random hash function h, which maps items into bins. And so if we have b bins, then this hash function will take an arbitrary string as input and output one of the indices of the bins in a random manner. And so we can repeat this many times, just filling up this hash table. And now the receiver can do the same operation for their set of all the y's. So for reasons that will become more clear here in a second, we'll use n over log n bins. And this will allow us to show with very high probability that no bin will exceed log n number of items. And now it's, instead of having to compare all pairwise between the two big sets, it's sufficient to only compare two binwise. So we compare each bin with each other. And since they use the same hash function, any items that are equal would be in the same bin. However, one important point to note is that the number of items that are in a bin reveals sort of how many collisions there are within a set. And this is very sensitive information. And so both parties need to pad the bins to the maximum possible size. However, as we said earlier, this is log n. And so overall, we still have n items combined between both sets. So now digging into the details, how do we compare two bins? We sort of just reduced the problem to itself. But now that these bins are much smaller, in this case log n, it might be more efficient just to do a brute force comparison between the two. So here we compare y2 against all the x's and so forth, and resulting in quadratic overhead within the single bin. Uh, and fortunately, we already talked about how you can compare a set against an item just using our private membership test here. And so the state of the art in semi-honest setting is approximately this. We just hash the bins and then compare binwise, except for the semi-honest setting, use a slightly more advanced hashing technique, which further reduces uh, the overhead. But I'll digress on that. So if that's the state of the art in the malicious or semi-honest setting, is this malicious secure, where the parties may arbitrarily deviate from the protocol specification? Well, it turns out that it's not. In this case, the biggest problem is with the sender. So here, they're supposed to provide the same set to each of these independent membership tests. However, they could easily provide different sets to each of the membership tests. And one immediate result of this is instead of having log elements to compare with, now, they now have log squared n elements. So that's a straight off the bat a violation of security. But even if we wanted to say like maybe allowing them to have more inputs is acceptable, uh, it's actually still not secure. And I'm not going to get into too much detail here, but to prove security, we have to show a simulator which takes the malicious behavior of the sender, sort of interprets it, and comes up with a valid another party which behaves honestly with input x star. So if we can convert malicious behavior into something that's approximately honest behavior, we say it's secure. But we show that you can't actually convert this sort of malicious behavior to any set x star that consistently outputs the correct intersection. So if allowing them to have too many inputs is a problem, a nice obvious solution would be to somehow restrict them to only provide using a consistent set between each of the membership tests. And so to do this, first we're going to unpack this membership test and recall that it's simply one oblivious transfer where the receiver picks up the corresponding encoding while the sender gets the full set of encodings. And we had repeated this 3 times, once for each membership test. And now before in the semi-honest protocol, what we had the sender do is take their 3 inputs and encode them under each of these different set of encodings and send them over. But now, crucially, we're going to reverse the direction of this protocol, where the sender now temporarily acts as the OT receiver, where they pick up an encoding of their element xn, where the other party, the receiver, has the full set of all possible encodings. We do this once for each of the x's. And now we're in this sort of symmetric setting where they each have an encoding under the other party and a full set of encoding themselves. And the crucial idea here is we further define this common encoding, ZAB, as the Z encoding under an A encoding and the Z under the B encoding XORed together. Now, each party can compute 9 of these common encodings, but crucially, they only have 3 different semantic values. In particular, let's take xn, for example. You can take the B encoding of xn and combine it with the 3 different A encodings of xn and come up with 3 common encodings, but they all have the same logical value. And by continuing this, we can generate this sort of square matrix of encodings. And likewise, the receiver can do the same operation. And now to complete the protocol, the sender takes all their common encodings and sends them over to the receiver. And the receiver can simply check whether for each of their y's, do they have a corresponding encoding, which matches one of the x tilde encodings. Now, there's a lot going on here, so let's sort of try to boil it down to an example. Let's say y2 equals xn. In this case, we only need to consider the top row of the x's and the first column of the y's. And we can see that these 2 rows and columns share one common encoding. That is the 1, 1 common encoding. And so since we have this x equals this y, then and they're under the same set of encodings, these encodings themselves will be equal, and this y will be output as part of the intersection. So we've just added a bunch of additional steps, and it seems to be correct, but why is it secure? Well, it's somewhat involved, but I'll try to give a highlight of what's going on here. So the simulator, we need to show that there's a simulator which can convert malicious behavior by the sender into some sort of semi-honest or consistent set X star, which then is forwarded to an ideal functionality. And this is just general paradigm how we prove security. And so the first thing this simulator does, it receives the possibly malicious incorrect messages of X tilde. And now it needs to figure out which of these encodings does it need to pay attention to. And the basic strategy is that for each of these xi terms, the simulator imagines that it might be in the intersection. And in this case, there must exist some yj term that was placed in this bin in one of the columns, and we place them in columns in a random order. And so the simulator plays like a mental game where it places this yj, which equals the corresponding xn, in one of the columns. And as before, this allows us to ignore the encodings that are not in the corresponding columns. And so now there's only one relevant xn encoding, which the simulator needs to test. And likewise, for these other locations, the simulator just plays this mental game, imagining that it's there, and then it allows them to eliminate many of the encodings, so they only need to consider one. And now the simulator simply checks whether these special encodings are actually correct, and if so, they forward the logical value onto this ideal functionality. You didn't follow that? Okay. But the point is, it's secure. And so now going back a little bit, let's look at how the overall protocol looks. We first hash the bins, and then within a single bin of size log n, we can do a quadratic overhead comparison. And since there's n over log n bins, the overall complexity is n log n. However, if we just ran this protocol, it would only be slightly faster than the previous state of the art. So we tried a little harder. And when you actually implement this, we need to ensure that like the concrete parameters of the bin sizes, it gets us a high amount of confidence that no bin will overflow. And it turns out that roughly four log n items per bin is how many dummy slots we need to have at least. And so that means that roughly 1 out of every 4 encodings is actually a real encoding. So we're encoding many things that don't actually correspond to anything. And what's maybe more important is that we actually have to communicate these dummy encodings over the network. So we're not using our network utilization very well. And so ideally, we'd be able to eliminate these dummy encodings. And to do this, first we have the sender simply not compute them. But if we just sent over these encodings, it would reveal the sort of the load of per item, the load of any given bin. And so we first define this X tilde term as all the real encodings, as I kind of just said. But now, crucially, we randomly shuffle all these encodings together so that there's no correlation between a given encoding and the bin that it was in. So now they can't correlate these things and figure out how many items are in a given bin. And by doing this, we get a 4x improvement in communication and running time, which turns out to be very crucial. And so our final protocol looks like this. The sender just encodes the items that they care about. The receiver does these dummy encodings, and then they simply check whether their encoding is in the set X tilde, resulting in n log n overhead overall. We also introduced several other. So the protocol I just introduced, we use in the random oracle model, where we need this random oracle, which is a slightly weaker model than the standard model, and it allows us to get better performance. And where we use the random oracle is in this encoding step. And so we show how you can actually replace this encoding step with a standard model, one that you can prove security in the standard model. However, to do this, we have to use many 1 out of 2 oblivious chancers, and it results in like a 20x increase in communication. But interestingly, is that this protocol, which isn't even our fastest one, is actually as fast or faster than the previous state-of-the-art protocol, which is also in the semi-honest, or also in the random oracle model. So we get the standard model sort of for free, and if you want to keep the random oracle, we're even faster. And we also introduce another variant which combines sort of commitments instead of this dual execution idea, and it gives some computation, communication trade-offs, which we'll leave to the paper. And so now an important question is it faster than the previous things? And it turns out to be quite a bit. So we compare to the Malicious-Secure Diffie-Hellman style approach, Di Cristofaro from 2010, and their approach, you had to do many exponentiations and also send over several zero-knowledge proofs. And so it's very computationally heavy, and that shows up with quite large running time, roughly like 4,000 seconds when you consider set sizes of 1 million. The Bloom filter approach from Eurocrypt earlier this year is faster, but still quite a bit slower than our protocol, which, for instance, takes 12 seconds for set sizes of 1 million items. And we're even able to scale up to sizes of 16 million items, which the previous protocols either took over 24 hours or just took too much memory in the case of the Bloom filter approach that our test bench couldn't do it. You can also consider some communication to computation trade-off. So shown here on the x-axis is the running time, while on the y-axis is the communication. And you can see that the Diffie-Hellman approach sends the least amount of data, but they also achieve a very large overhead. In particular, it's roughly like 450 times slower than our protocol, but sends 8 times less. And we're also faster than the Bloom filter one, and we send less data. And this just, it comes from the fact that a Bloom filter is quite large compared to our encoding technique. And we can also compare to the state-of-the-art semi-honest protocol, and somewhat to our surprise, we're only 3 times slower than the semi-honest protocol, and this in communication and computation. And this comes from the fact that our protocol requires big O n oblivious transfers, but we send n log n amount of data in computation, while the state-of-the-art semi-honest protocol does the same number of T's, but it gets away with sending less and computing less by using a better hashing technique. And this is known as cuckoo hashing, where we investigated this approach in the malicious setting, and it proved that the amount of overhead that you'd get to make cuckoo hashing malicious secure was quite significant. And so we chose to use a different hashing technique, which in practice, while asymptotically worse, actually gives better performance. And finally, we can also compare to the naive protocol, where this one is completely insecure, and you simply just hash your elements and then send them over to the other party. It's very vulnerable to a brute force attack, but we show that we're only slightly slower than like 8x slower or so, slower than the naive approach. So to get malicious security, 8x overhead is not too bad in our opinion. And then I guess I have a little extra time, so I want to talk about future work. We could investigate how you can make this cuckoo hashing approach, which is asymptotically better, more efficient. And then we also consider more rich functionalities, such as set cardinality is used in some places where you just want to learn how big is the intersection. You could also consider PSI with associated data, so more SQL key value pair type intersection. Multi-party computation, which Neil will be talking about shortly, but there's still many variants of this problem that are wide open, such as only revealing the intersection if it's above some threshold. Composable PSI, where you might want to do a union in the middle between multiple parties and then do a final intersection. And you could also consider PSI as a pre-processing phase to other secure computation algorithms, such as machine learning, where you might want to join 2 different data sets that are split between several of the different parties, and then run machine learning algorithms on top of the joined data. So these are all exciting future works, which are waiting for our people to solve. So that's it. So thank you.
Yeah, hi, thank you. So I have a petty comment and then an actual question.
Sure.
So my petty comment is that it is not illegal to be registered to vote in multiple states. It's only illegal to vote in multiple states.
Okay,
So,
thank you.
Anyway, that's my petty comment. And my actual question is, what happens when you're unlucky with the hash function and you overflow one of the bins?
Yeah, so this is sort of a classic balls and bins analysis, and you can easily show that we just bound the probability of any bin overflowing is negligible in our security parameter, which we set to like 2 to the power negative 124. So it's like 1 in a trillion probability.
Okay, so it just doesn't happen.
Just doesn't happen. Yeah. And that's where these dummy encodings come in that we make sure that they're full enough.
Saudi Griazi from San Diego. Great talk, by the way. I wanted to ask, when you talk about the shuffling the beans, was it shuffling the beans or items within the bean?
Oh, yeah, items within a bin. Yeah.
Within the
So
bin.
you take all the common encodings and you shuffle them together and then send the shuffled encodings to the other
And
person.
doesn't reveal any information about the collisions
Yeah,
from the collisions?
that's correct. Because there's no they learn for each item that's in the intersection, they learn that it was in some bin, but they already know that. And for all the encodings that aren't in the intersection, they don't know which bin they were in. They only know that there's in total n log n total encodings. And
So
so
the
that
histogram of like number of items within a bean, that doesn't reveal anything?
that would reveal any information, but the receiver can't reconstruct that histogram because there's no correlation between a given encoding and which bin it's from. We break that correlation, so you can't like create this histogram.
Okay. And the second question is, the matrix creation reminded me of OT extension. So have you investigated using Malicious-Secure OT extension in your work?
Yeah, everything here is OT extension. This would not be very fast if we use like public key based OT.
No, I'm comparing semi-honest OT extension with Malicious-Secure.
Oh, yeah. The overhead between semi-honest and malicious. Yeah, some of these newest protocols are quite efficient. The KKRT OT protocol, which is one out of N, is only slightly faster than the malicious version of uh, the OOS 16 paper. So it's very small difference.
Okay, thank you.